Hi, I'm Lauren Saponaro, and this is my Physics 2211 Lab 4 presentation. So just as an introduction, the purpose of the lab was to analyze the motion and energy transfer of a spring mass system using Tracker to analyze the given video and a computational model to compare the predicted and actual motion of the system. And the system included everything, the mass, spring, and earth, and there were no surroundings. And the results were that the seemingly complicated and unpredictable motion of a spring mass system actually follows a logical pattern that can be explained through the following fundamental principles, which are the energy principle, gravitational potential energy, kinetic energy, spring potential energy, spring force, oscillation, and Newton's second law. So here's what my tracker data looked like. As you can see, I set up the axes so that the origin is at the point that the spring is fixed to, and then I set the calibration stick to be 0.7 meters because that was the given length of the spring or the string. And on the side, you can see that the values that I got by tracking the position. And here's the beginning of my code for the mass. It was given that it was 0.402. And then for position, I just copied the position vector at the first frame that I tracked, so at t equals 0. And then that was that. And then the velocity vector in the beginning was starting from rest, so I just set that equal to 0. And then at the bottom, the t equals 0 is where we're starting, and delta t is 1 over 210. And for this part of the code, I basically just boxed everything that I changed, but I added the 9.8, which is a gravitational constant, and then I also added the spring constant, which I calculated from the formulas I showed in the beginning. And I also have the relaxed length of the spring, which I found using those same equations. And then here I just plugged in some different terms to specify that the length equals the position of the ball minus the spring position. And I also specified that L hat is just a unit vector of L, and that S is equal to, it's the stretch of the spring, and it's the magnitude of L minus the initial length of L. And I also added some different formulas for the energies. And then again, in the blue boxes, what I edited, so it was time was under 9.429 seconds because that was the final frame that I tracked. And then I'm using the tracker again here to define the initial energies. And I set the gravitational force, spring force, net force, ball velocity, ball position, and just updated them using the principles that the code told me to. And here's the final part of the code, and I just plugged in like all the different values for the calculations. And then here are the results. It came up with a model, like the one here on the side on the right, and then on the left is the energy versus time graph. And here's a better look at that. And it basically shows that the change of energy is equal to the change in kinetic energy plus the change of potential energy. And this is good because this satisfies the energy principle. And these are the x position and y position versus time graphs. And for both of them, I calculated the period of oscillation. And I attained these by going into Tracker, and I saw what time each was at and counted like 3 or 4 oscillations. And then I divided that by the number of oscillations I chose. And they came up with pretty similar periods. So the x was 1.381 seconds, and the y was 1.3095 seconds. And so these were pretty consistent. And then so in conclusion, the model and tracker data are almost identical. and the computational model did an excellent job of predicting the motion of the spring mass system. And I would like to just point out that there is you could account for error because the code does not account for the air resistance or drag. So the predicted motion won't be 100% accurate, but it was pretty close.